In this video, we're going to study isomers. Isomers are molecules that have the same molecular formula, but their atoms have a different arrangement. So they basically have the same atomic composition. They're made of the same atoms, same type and number of atoms, but they're arranged in different ways such that they're actually different molecules. So you can look at isomers as there being two types of isomers. There are isomers called constitutional isomers, which are also called structural isomers, and then also stereoisomers. And those stereoisomers can be broken down into diastereomers and enantiomers. And so we're going to focus on constitutional isomers first, and then afterwards we'll go take a look at stereoisomers as diastereomers and as enantiomers as well. There are other types of isomers that exist, but in grade 12 chemistry, these are the basics you need to know, and that will give you a good enough understanding to understand other isomers later on. So we'll start off with constitutional or structural isomers. These are molecules that have the same molecular formula, but their atoms are bonded together in a different sequence. So they actually have a different bonding sequence. The atoms have moved positions. And so because the atoms are in different positions, the physical properties of these isomers will actually be different from each other because that leads to different shapes, which leads to sort of forces being distributed differently, like different types, different amount of LDF, for example. And that leads to different, like as I said, physical properties like boiling point. So let's take a look at these molecules here. These molecules, hexane, 2-methylpentane, 3-methylpentane, and 2,2-dimethylbutane. These are all isomers of each other. I know that because if I were to look at their molecular formula, C6H, and if you count everything, H14, they all have C6H14. They all have C6H14. So the same atoms, same composition, but they're arranged differently. In hexane, they're arranged as a chain. In 2-methylpentane, one of the carbon-hydrogen groups is moved on to somewhere in the middle of the chain, and now you have this 5-parent chain with a substituent here. In 3-methylpentane, well, we simply took this and moved it over one, and we have the substituent on carbon number 3. And then in 2,2-dimethylbutane, well, we took off another carbon from the chain and put it as in a substituent form here. And so now we have sort of this shape here instead. And notice that even though they're the same molecular formulas, we have the atoms placed in different sequences in different areas in the molecule. We have different properties. So hexane has a boiling point of 69, whereas 2-methylpentane is 60, 3-methylpentane is 58, and then 2,2-dimethylbutane is 50. And as you know from the first unit, because these are all hydrocarbons, non-polar, all they have is LDF, so the difference must be in the LDF, which is probably due to their shape. Remember, linear has more surface area for more LDF, whereas something that's less linear, more branched, for example, has a little bit less surface area. And because there's less surface area, there's less LDF contact happening. So again, to check that these were all constitutional isomers of each other, I saw that they all had the same molecular formula and that their atoms were arranged in different bonding sequences. Just to double check that they actually are different, I like to name the molecule. If they have a different name, but they have the same formula, then they're likely going to be constitutional isomers. So how do I identify if molecules are constitutional isomers? First, check if they have the same molecular formula, and then see if they actually have a different bonding sequence. So be sure that they also have different names, because sometimes, for example, if I draw this, you might think, oh, well, this one's a different one altogether. It's different from all the ones there. But in reality, this is also just 2-methylpentane, just drawn sort of flipped, but it's the same molecule. You can just grab the molecule and flip it around. It's the same thing. So be sure that the name is different. Otherwise, you've just drawn the same molecule twice. So you can try the practice problems here. You can try to identify which of the following are structural isomers of one another. You can pause the video to try it out yourself first to think about how you would approach this, and then you can unpause to see if you're on the right path with the strategies I teach you. So what I would do first is I would try to find the molecular formula of each substance here. Notice that they're all single bonds. So for A, for example, there's no double bonds. I know it's an alkane. There's 1, 2, 3, 4, 5, 6 carbons. So it's C6H14 because it's an alkane, CnH2n plus 2. Or you could just draw out all the H's and just count them. Here we have 1, 2, 3, 4, 5, 6, 7 carbons. So C7H16. Here we have 1, 2, 3, 4, 5, 6, 7 carbons. An alkane again, so C7H16. Here we have 1, 2, 3, 4, 5, 6, 7 carbons, so C7H16. Here we have 1, 2, 3, 4, 5, 6, 7 carbons. Be careful here. This is a cyclical molecule. So the general formula is CnH2n, so C7H14. And then here we have 1, 2, 3, 4, 5, 6, 7, C7H16. So now that I've done this, I can go and eliminate the ones that would not be structural isomers. And those are the ones that have different molecular formulas. So we know A would not fit because it's C6H14. And we also know E would not fit because it's C7H14. So A and E are not in there. So really now in the runnings, we have B, C, F, and D. I just want to make sure these are all actually different structural isomers of each other. Like they have the same molecular formula. And I just make sure they're actually different molecules by going to name them. So for example, here I have 1, 2, 3, 4, 5, 6, 2-methyl hexane. Here I have 1, 2, 3, 4, 5. So 2, 3 dimethyl pentane. Over here we have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. So this is the longer chain. And so this is 1, 2, 3, 3-methyl hexane. And here I have 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it doesn't really matter which way I go. Here I have 3-ethyl pentane. So these all have different names. That means that they are distinct molecules. They have the same molecular formula. And the way they differ is that they have different bonding arrangements, different bonding sequence. So for example, over here, this 2-methyl hexane, the methyl group is on carbon 2, but here the methyl group is on carbon number 3. So the structural isomers or constitutional isomers of each other are B, C, D, and F, not A and E. Okay, next up, let's try the following question. You can try it yourself first and then see if you're on the right track by unpausing the video when you're done. So true or false, the molecules below are structural isomers of each other. So again, first step is let's just find their molecular formulas. We got alkanes we're dealing with here. C, so 1, 2, 3, 4, 5, 6, 7. C7H16. Here, 1, 2, 3, 4, 5, 6, 7. C7H16. So you might think, yes, maybe they are structural isomers because they have the same molecular formula, but let's check if they actually have a different bonding arrangement. If you look here, if you think about it, this 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, this is our parent chain here, okay? This is our parent chain over here, and there's an ethyl group there, an ethyl group here too. Notice that they're on the same carbon, 1, 2, 3, 1, 2, 3. So these are actually both the same molecule. They're both 3-ethyl, 1, 2, 3, 4, 5, pentane. So this is actually false. They're not isomers of each other. They are the same molecule. To be isomers, you actually have to be different molecules. You have to have a different bonding arrangement. I know you might think, well, aren't they different because this points down and this points up? No, because when you have a single bond, the single bond can actually rotate. It rotates. And so as it rotates, sometimes the bond faces up, sometimes it faces down, but it's the same thing. It's like if I were to turn my pencil around, sometimes the pencil lead might point towards you as I'm rotating it, and then it points away from you, but it's still the same pencil nonetheless. So this is the same thing. It's rotating in 3D space, especially around the single bond. Single bonds just spin around themselves. And so sometimes that substituent points up, sometimes it points down, but it's the same molecule. Maybe you just got a snapshot of them doing different things. Like if you're taking a picture of me, you might get a picture of me smiling sometimes, and other times I'm frowning, but it's still the same face. I'm still the same person. There's not an isomer of me. Okay, so let's do a few more practice problems here. And then in the next video, we're going to take a look at how to draw structural isomers of different molecules. But for now, we're going to finish up with these problems here. So which of the following are structural isomers of each other? So you can try this one out and see if you're on the right path. So again, as usual, I would try to find the molecular formula and really try to eliminate some choices and some options. So for for molecule number 1, we have 1, 2, 3, 4, 5, 6 carbons, C6. I'm going to just count the carbons first because that'll allow me to actually eliminate stuff. 1, 2, 3, 4, 5, C5. Okay. 1, 2, 3, 4, 5, C5. All right. 1, 2, 3, 4, 5, C5. Notice by just counting the carbons, I got rid of option number 1. So option number 1 cannot be the case because it has 6 carbons, right? 1, 2, 3, 4, 5, 6. It's not part of it. So that means I can delete A and cross out B from my choices. And now I'm only choosing between 3 different choices. So now I'm going to go and find the formulas, the rest of the molecular formula, the H's, and then from there I can make more decisive conclusions. So if you want to just draw in the H's, you know you need 2 H's here, 2 H's here, 2 H's here, 2 H's here. Here you just need 1 H, and on the end here you have 1, 2, 3 H's. And I believe that makes sense because it should be CnH2n. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So C5H10. Okay, so we have C5H10. Let's next try out this molecule here. So here you just need 2 H's. Here you need 1 H, 1 H, 1 H, and then 3 H's. And so that would be C5H, 1, 2, 3, 4, 5, 6, 7. Oh, so let me try that again. 1, 2, 3, 4, 5, 6, 7, 8. C5H8. And I believe that makes sense because if you had the alkane, just a regular alkane, you have CnH2n plus 2. You do this, it takes away a 2 H's. You add this, takes away another 2 H's. So by now you're at H2n minus 2, which is C5H8. That makes sense. So, okay, we know that 3 and 4 can't be together in an answer. So right away, that gets rid of option C. Now we just need to see, is it 2 and 3 or 2 and 4 that are isomers of each other? So let's take a look. Let's count our H's. We need 2 H's here, 2 H's here, 2 H's here. Here we just need 1 H, 1, 2, 3, 4. Here we just need 1 H as well. So it's 1, 2, 3, 4, 5, 6, 7, 8. C5H8, which makes sense because the cyclic is a point of unsaturation, so to speak. Not really, but it takes away 2 H's because you have to connect the ends. And so does a double bond, which is a point of unsaturation. So we're back at this general formula here. So really, C5H8 is 2 and 3, not C5H10. So it's not 2 and 4, it's D, 2 and 3. And so that's how you would solve a problem like that. But notice you do want to develop a strategy to kind of go more quickly through this. Sometimes you don't have to do the entire problem. Like there was no point in me counting all the H's right away. I could have just started off with the C's and then eliminated some there, and right away I can delete or eliminate some of the choices I'm dealing with, and it just makes my life a little bit easier. So let's do the last problem here together. If you can try it yourself first, then unpause the video, see if you're on the right track. Which of the following are structural isomers of each other? So I'm going to start off by just acknowledging that these are all alkanes. So for the most part, they have the CnH2n plus 2, except for the cyclical one. But I don't have to go recount everything. These are all alkanes, so they're all CnH2n plus 2. And then the ring is a CnH2n. So Here I have 1, 2, 3, 4, 5, 6, 7, 8. So that's C8H18. Here we have 1, 2, 3, 4, 5, 6, 7. C7H16. For D, I have 1, 2, 3, 4, 5, 6, 7, 8. C8H18. For E, I have 1, 2, 3, 4, 5, 6, 7, 8. C8H18. For F, I have 1, 2, 3, 4, 5, 6, 7, 8. C8H18. And then for C, I have 1, 2, 3, 4, 5, 6, 7, 8. C8H16. So right away I can eliminate C and B because they have different molecular formulas. Now I just want to make sure that these molecules all actually have a different bonding arrangement. In other words, do they all have different names to show they have different bonding arrangements, and they're not just rotations of each other. So I'm just going to go ahead and name them, and that will confirm it. So A is 1, 2, 3, 4, 5, 6. So 4, 5, 6. So I have 2,4 dimethyl hexane, 2,4 dimethyl hexane. For D, I have, let's see, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So the best route to go is probably this route over here, because when you have equivalent parent chains, you want to try to get the parent chain with the most substituents on it. That'll be your parent chain. So we have 1, 2, 3, 4, 5. So in carbon number 2 and 3, we have substituents. So we have a 3 ethyl. Let me make sure that's right. 1, 2, 3, 4, 5. Yeah, 3 ethyl, 2 methyl, and then pentane. Let's try E. E is 1, 2, 3, 4, 5. Doesn't really matter where we go. 1, 2, 3, 4, 5. So we have 2, 3, 4 trimethyl. 2, 3, 4 trimethyl. And then 1, 2, 3, 4 pentane. So far, A, D, and E are definitely structural isomers of each other. We're just going to try F now to see if it is different than the rest. So 1, 2, 3, 4. That's our longest chain. 1, 2, 3, 4. Yep, that's right. So on carbon, it doesn't really matter which way we go. So this could be 1, 2, 3, 4. So we have 2, 2. So 1, 2, 3, 3, 3 tetra methyl butane. And since it has a different name, that means that we have these as our structural isomers of each other, but not B and not C. And so in this video, we saw the idea of isomers, what isomers are. We saw there's two types of isomers, constitutional and stereoisomers, which can be further divided into diastereomers and enantiomers. We focused on constitutional isomers first. We defined them and saw how to identify them if we were given pictures, and then also justify our ability to identify them with evidence. And we did a variety of practice problems to make sure that we could identify constitutional isomers and those that did not belong as constitutional isomers. In the next video, we're going to take a look at how to draw constitutional or structural isomers given a certain formula or name.